Welcome back to the deep dive. Today we are, we're going to break your brain a little bit.
Just a little bit.
Okay, maybe a lot, and I don't say that lightly. We are looking at a topic that takes the fundamental rules of reality, things you've taken for granted since you took your first step, and asks, are you absolutely sure about that?
Yeah, I'd say we're taking the physics engine of reality and trying to run it in reverse.
Yeah.
It's a complete inversion of how we perceive the physical world.
Fair point.
Mm-hmm.
We're looking at a stack of video experiments from a content creator named Levelheaded William. And our mission today isn't just to recount some cool science tricks you can do in your garage.
Right.
It's to understand a completely different operating system for the world we live in. We're talking about a framework where gravity isn't a pull, weight isn't a property of matter, and the ground you're standing on right now might not be as stationary as it feels.
It's a fascinating theoretical challenge. The source material basically argues that what we call gravity is actually a misunderstood effect of acceleration. And the way they get there is through these incredibly stripped-down DIY experiments. I mean, we aren't looking at data from the Large Hadron Collider here.
No, definitely not. We're talking about cargo vans, plastic water bottles, helium balloons, and smartphone sensors.
It's garage science. But the implications are massive. It's almost disarming how simple the tools are when you consider the size of the claim.
Massive is the right word. And I want to set the stage here early on because the methodology of the source is key.
Exactly. The core method we're going to see over and over again in these videos is a basic comparison.
Right, comparing two states.
The source asks us to look at how objects behave first when they are connected to the Earth, like sitting on a table or standing on the floor, and second, when they are in free fall.
And just a quick disclaimer before we launch into the deep dive here. We are playing the role of impartial observers today.
Strictly neutral.
Yes, strictly neutral. We are unpacking the logic and the findings, strictly as presented in the Levelheaded William videos. We aren't here to endorse these viewpoints or get into a debate about standard textbooks.
We just want to see if we can understand the specific argument from the inside out, to see how the pieces of their puzzle fit together.
Exactly. We want to see if the internal logic holds up on its own terms. And interestingly enough, it all starts with something we think we understand intuitively: buoyancy.
Right, floating and sinking.
Okay, so let's get into the first experiment. This one really stuck with me because it's just so counterintuitive.
The water tank.
Yes. Imagine a clear, rectangular container filled with water. Inside this container, there are two objects. You have a steel ball and you have a ping pong ball.
So it's a study in density, high-density steel versus low-density air-filled plastic.
Right. The experimenter takes this container and accelerates it sharply to the right.
Okay.
Now pause for a second. If I'm in the passenger seat of a car and the driver floors it, I get slammed back into the seat. My coffee spills backward.
Standard inertia.
Right. So my intuition says both balls should fly to the back of the container.
And for the steel ball, that's exactly what happens. It stays at the back left of the container while the container moves right.
But the ping pong ball does something weird.
It flies forward.
Yes. It shoots in the same direction as the acceleration. If you push the tank right, the ping pong ball goes right.
Which feels like it violates the laws of physics entirely.
Why would an object chase the acceleration? It makes no sense at first glance.
It's actually perfectly consistent, but you have to stop looking at the balls and look at the water. Water has mass. It's heavy.
So when you shove that tank to the right,
The water resists that motion. It piles up against the back wall.
like a slosh.
Precisely. That slosh creates a pressure gradient. You have high pressure at the back of the tank where the water is bunching up and low pressure at the front.
Okay, I'm with you.
The water is effectively squeezing everything toward the front. The steel ball is dense enough to fight that squeeze and stay back. But the ping pong ball is light.
The water pressure wins.
It wins, and it squirts the ball forward toward the low pressure zone.
So the source calls this true motion.
Right. Yes. The argument is that the steel ball isn't really moving backward. It's just lazy. It has inertia. It's staying put while the container moves around it.
That's apparent motion.
Exactly. But the ping pong ball is being actively pushed by the pressure gradient. That is its true motion.
So this is the major insight for this first segment. Buoyancy isn't a magical floating power. Buoyancy is just a pressure difference, pushing less dense stuff away from the high pressure zone.
That's it. And then the source takes this concept out of the water tank and puts it into a vehicle.
The cargo van experiment, this is where it started to click for me visually.
It's a classic way to visualize this. You can picture it perfectly.
So you're inside the back of a cargo van, no windows, just a metal box. You have a helium balloon tied to the floor with a string and an apple sitting on the floor next to it.
And the driver slams on the gas.
Again, your body tells you, I'm going back. And the apple does roll back. It hits the back doors.
But the balloon leans forward.
Right. It leans toward the windshield. It actually pulls against the string in the direction the van is moving.
It's the exact same mechanics as the water tank. The air inside the van is the fluid. When the van accelerates forward, the air rushes to the back.
Because air has mass.
Yes, it creates a high-pressure zone at the rear doors and a low-pressure zone at the windshield. That dense wall of air at the back squeezes the lighter-than-air balloon forward.
So here's where the source makes the big leap. He connects this straightforward observation directly to the Earth.
This is the pivot point of the entire theory. The source argues, look, we see buoyancy on Earth every day. Helium balloons go up, air bubbles in water go up.
And we just established that for buoyancy to happen, you need a pressure gradient, a squeeze.
Right, and to get a squeeze, you need acceleration on a contained system.
So if balloons go up on Earth,
Then the pressure must be highest at the bottom and lowest at the top.
which we know is true, atmospheric pressure is higher at sea level than it is on Mount Everest.
Correct, but the source asks why. In the van, the pressure gradient was caused strictly by the van accelerating forward.
Right.
On Earth, since the buoyant direction is up, the source argues the Earth itself must be accelerating up.
That's the core claim. The Earth is effectively a massive cargo van flooring it towards the sky, constantly.
And that vertical acceleration creates the pressure gradient that pushes the air down and squeezes the balloons up.
It's a wild mental image.
Yeah.
But to prove it, the source says we have to look at what happens when that acceleration stops.
Which brings us to the free fall anomaly.
Yes, this is where the source really tries to dismantle the idea of gravity as a downward pull.
These experiments are visually compelling. The source posits a core question. If weight and buoyancy are permanent properties of matter, if they're just things that fundamentally exist, why do they vanish the moment you drop the container?
Let's look at the water bottle test. This one is something you could do in your kitchen sink, though maybe don't make a mess, because I tried it and got water everywhere.
Please don't flood the studio.
I'll try not to. So he takes a standard plastic water bottle and drills 3 holes vertically, top, middle, bottom. He fills it with water and holds it up.
And naturally, gravity or pressure does its work. Water sprays out of the holes
The bottom stream shoots the furthest.
because it has the most weight of water pressing down on it. It's a visual map of pressure. The deeper you go, the higher the pressure.
Then he drops the bottle, he lets go into free fall. And I watched this clip 3 times because it looks almost like CGI, but it's real life. The water just stops.
It cuts off instantly.
It doesn't dribble, it doesn't slow down. The streams retract and the water stays perfectly still inside the bottle as it falls through the air.
Now, standard physics explains this as weightlessness. Everything is falling at the same rate. The water, the bottle, the air, so the water isn't pushing against the side of the bottle anymore.
But the source interprets this differently. How so?
The source says, look, if gravity were a distinct force pulling the water down, that force should still be there. The water should still be under pressure.
Because it's still mass in a gravity field.
Exactly. The fact that the pressure gradient evaporates instantly suggests that the cause of the pressure, the acceleration, has stopped.
So in this worldview, when you drop the bottle, you aren't letting gravity take over. You are disconnecting it from the engine. You're stepping off the gas pedal.
He argues that free fall isn't a state of acceleration. It's a state of rest. The bottle is just floating there, and the Earth is no longer pushing on it.
He shows this with the air bubble, too.
Right. The clear tube of water. On the table, the bubble fights to get to the top. It's desperate to rise.
That in free fall.
The bubble stops rising. It just hovers in the center of the tube, turning into a perfect sphere. No up, no down, just suspension.
And the slinky. We have to mention the slinky. That was maybe the clearest example of this force disappearing.
The helium balloon on the slinky, this is brilliant in its simplicity. He has a box. Inside, a slinky is attached to the floor, and a helium balloon is tied to the top of the slinky.
So on the table, the balloon wants to go up, right, and stretches the slinky out. You can physically see the tension in the coils.
Visually, you see the force. The balloon is pulling, the slinky is resisting.
But then he drops the box. And snap. The slinky retracts instantly. The balloon stops pulling entirely.
It looks like someone just cut the power cord to physics.
And that's his argument. He says, I removed the contact with the Earth, and all the forces, buoyancy, weight, Tension disappeared.
If gravity were a separate force pulling on that balloon or that slinky, why does it stop acting the moment contact is broken?
It's a really compelling question. He's arguing that the only time forces exist is when the object is in contact with the ground, or the accelerator as he frames it.
But standard intuition fights this.
Right, here's the problem I initially had. If I jump off a diving board, I don't feel like I'm floating at rest. I feel like I'm rushing downwards. I feel motion. I feel the wind in my face.
That's subjective, though. Your stomach dropping is a biological reaction to inner ear changes. The wind is just resistance. The source wants hard data to strip away the biology.
So he brings out the smartphone, specifically the digital accelerometer.
I love that we can do physics with a phone now.
There's an app for everything, even questioning the fundamental nature of reality.
It's incredible. So for you listening who might not know, an accelerometer measures g-force. It measures acceleration. When the phone is sitting on your desk right now, what does it read?
1G.
1g, which we ignore because we're used to it. But 1g is a measurement of acceleration. Technically, it means we are accelerating at 9.8 meters per second squared.
Or in the standard model, that gravity is pulling us down with that equivalent force.
That's the standard interpretation. But then the source takes the phone and drops it. It goes into free fall, and the reading drops to 0g.
Zero. Just flat zero.
Now, pause here. This is the crux of the argument. Standard physics says 0g means you are falling, so you don't feel your weight.
But the source takes the reading literally.
He asks, if I am accelerating towards the ground at high speed, why does my acceleration meter read 0?
That is a semantic trip. Because if I floor it in my car, the meter goes up. If I'm in a rocket launching, the meter goes up. Acceleration usually registers as an increase in g.
Precisely. The source argues that 0g means exactly what it says. No acceleration is happening. The phone in free fall is the only thing that isn't moving.
Which implies that the phone sitting on the table, the one reading 1G, is the one doing the actual moving.
It's essentially the Einstein in an elevator problem. If you were in a closed box in deep space, and that box started accelerating upwards at 9.8 meters per second squared, you would feel your feet press against the floor.
You would feel weight.
Right. And if you dropped a pen, it would appear to fall to the floor. The source is saying that's not a metaphor. That's literally what Earth is doing.
But wait. The app creates a bit of a puzzle here. There's a vector tab that shows the direction of the force. And this part honestly confused me the first time I watched it because the arrow seemed backward.
It's tricky because of how phone sensors work. Think of it like a cup of coffee inside the phone. If you shove the phone to the right, the liquid sloshes to the left.
Like the coffee in my cup. If I push the cup forward too fast, the coffee spills on my lap.
Exactly. So the sensor registers the slosh, not the push. It's inverted. If you push the phone right, the vector arrow points left.
Okay, I'm with you. So the arrow points opposite to the actual acceleration.
So the source puts the phone on the table. The arrow points down.
Which feels normal. Gravity is down.
Oh, remember, the arrow is inverted. If the arrow points down, that means the actual force being applied to the phone is coming from
the bottom. Pushing up.
Bingo.
Rip.
The source argues that the down arrow is just the sensor's inertia reacting to the Earth pushing it up.
So the data on the screen, if you accept the inversion logic of the sensor, literally says I am being accelerated upward.
And he backs this up visually with the flame experiment. This one is poetic. The rule he establishes is flames always follow the direction of the force.
He shows this with a centrifuge, right?
Yes. He spins a centrifuge, and the flame points inward toward the center. He accelerates the van, the flame points forward toward the windshield.
Because the flame is lighter than air, it behaves exactly like the helium balloon. It points in the direction of the acceleration.
So he looks at a standard candle sitting on a table. The flame points up.
Conclusion, the force is up. The Earth is pushing the air up, squeezing the flame into that upward spike.
And let me guess, what happens when he drops the candle?
The flame goes spherical. It becomes a little ball of fire. No direction. No force.
It's a very consistent internal logic. It all circles back to this core idea that weight isn't what we think it is.
No, and the source is very explicit about this. Weight is not a property of matter. It's an event. It's an interaction.
There's a rock experiment that demonstrated this definition really nicely.
The 2-pound rock. He uses springs to define what weight actually is. First, he puts the rock on a compression spring like a mattress spring.
The rock squashes the spring down.
We call that weight. But then he drops the whole setup. In free fall, the spring expands. It actively pushes the rock away.
Because the rock stops pushing down.
Right. Then he uses a hanging scale, a retention spring. On the table, the rock stretches the spring down. In free fall, the spring snaps back up. pulling the rock with it.
So the rock isn't pulling anymore.
Not anymore. The source's definition is that weight is simply the resistance created by the Earth pushing against an object.
If the floor pushes you up, your inertia resists, and you feel heavy.
Remove the floor, enter free fall, and you can't have resistance against nothing. So weight completely vanishes.
This leads us to arguably the most surprising political twist of the source material. You'd expect this to be a typical flat Earth theory, right?
Usually, yes. If you're questioning gravity on the internet, you're usually talking about a flat, stationary disk.
But the source actually argues vigorously against the standard flat Earth model of a motionless plane.
It's a fascinating moment of infighting in alternative physics. The source says, you simply cannot have a motionless Earth.
Why not?
Because of buoyancy. The source is adamant. We prove that buoyancy requires a pressure gradient, and a gradient requires acceleration.
Right.
If the Earth were a motionless disk, the air wouldn't settle into dense layers. There would be no up or down for bubbles or balloons. Everything would just float chaotically.
So to explain why the bubble rises, the Earth must be moving.
It must be constantly accelerating upwards. That is the only way, according to Levelheaded William, to account for the physical reality we observe.
Which completely inverts our relationship with the ground. We usually think, I am sticking to the Earth because gravity pulls me. This model says, I am stuck to the Earth because it is constantly ramming into my feet.
And that's why you get tired standing up for a long time. You are constantly fighting an acceleration. It's like doing a leg press forever.
There was one final experiment that really drove home how easily our eyes deceive us with this stuff. The ruler in the box.
The relativity perception. This is the don't trust your eyes segment.
He has a ruler sliding through a slot in a box, and he simply asks the viewer, what is moving?
If you mount the camera to the box, it looks like the ruler is sliding down. But if you mount the camera to the ruler, it looks like the box is sliding up.
Visually, they are totally identical. You cannot distinguish between the two motions just by looking.
And that's the trap. The source argues that we look at the horizon, we look at the ground, and we say, well, it looks still.
But just like the ruler, you can't judge motion from inside the reference frame. You need external data.
And for him, the external data is the fluid. The behavior of the water, that pressure gradient, the way it sloshes, is the proof that the container is moving.
He's saying the water doesn't lie. Your eyes might, but the water doesn't.
So where does this leave us? We've looked at the water bottles, the accelerometers, the flames. It's a highly comprehensive system.
It is, and whether you accept the conclusion or not, the value here is in the exercise. It forces you to realize that raw data always requires interpretation.
We all see the apple fall. That is the baseline data point.
Right. Newton looks at it and sees a pole. Einstein looks at it and sees curved space-time. And level-headed William sees the floor rushing up to meet the apple.
The raw data, the time it takes to hit the ground, the impact, the bruises on the apple, is mathematically identical in all three cases.
It's the story we tell about the data that changes.
Exactly. And this specific story, the upward acceleration model, is a masterclass in recontextualizing sensory input. It takes the feeling of weight, which we take completely for granted, and asks, what if this is active?
It makes you hyper-aware of your own body. Like right now, sitting in this chair, I feel the pressure on my back and my legs.
In standard physics, that's just the normal force resisting gravity. In this model, that's the chair actively accelerating you upwards, keeping you ahead of the void.
It's a bit terrifying, honestly, when you picture it.
It certainly gives grounded a whole new meaning.
It really does. So next time you're in an elevator, and this is the classic real-world test for you listening, when it starts going up and you feel that extra heaviness in your legs.
Think about the cargo van.
Are you getting heavier, or is the floor just pushing you harder?
And conversely, when the elevator goes down and you feel that little lift in your stomach, are you falling? Or is the Earth just backing away from you for a split second?
That is the question I want to leave everyone with today. We rely so much on feeling weight to define our reality. But if that sensation fundamentally requires contact, if you only exist as a weighted object when you actually touch the ground, are you being pulled down or are you being pushed up?
It's all a matter of your frame of reference.
And on that note, try not to think about it too much while you're driving.
Good advice. Thanks for taking the plunge with us. We'll see you on the next one.
Keep questioning the obvious.